Okay, so I'm going to walk you very briefly through, let me just make sure the sound is on. Sound is on. I'm going to walk you very briefly through the MiniProject 2. So you'll start with, don't mind the name. Once upon a time, this was the first of the two projects. The order between the caching and the out of order isn't that deep. Concurrent, that's how it goes. You got your tarball, and so let's start by untarring it. So extract the zip file, and you'll get a directory called student version. So you go into student version, and this is what you'll see. You'll see a makefile. We'll take a look at that in just a second. You'll see, importantly, nmm-ccm.working.testout. That is the reference output. Note that it is not going to be verbatim identical. We'll talk about that in a second. But that will give you the appropriate reference for what should be happening. And all of your modifications will go in your code here, .c. So, but you'll spend a lot of your time on this project mostly just reading. There's not a lot of code to write. But let's start with taking a look at the makefile. So if you take a look at the makefile, here's what you got. It builds a little cache simulator. Now it's a very specific cache simulator in that it only does naive matrix multiplication. So that's the only thing it models. It only models the data side cache, doesn't do anything for instructions. But within that data side hierarchy, it can do any number of L1, L2, configurations. You can set it up in a bunch of different ways. So you can see below, if when you do make a test, you'll run it on several different potential cache hierarchies. So each of these is a different configuration. I'll give you some sense of it. You can go read the code later to get a sense of what the numbers are, but you can see this very first one. So this, we get to specify the size of the matrix. So in this case, it's going to be a 2 by 2. And you're going to specify that, in fact, the only layer that exists is main memory. And so we don't really care about the configuration of main memory. It's main memory is always going to be the same. And you can see here in other configurations that we have an L2, an L1, and main memory. So you can see it's sort of defining this hierarchy back from main memory all the way down to whatever the smallest levels of cache are. So you can build an arbitrarily deep cache hierarchy and make it different sizes. So you can see here the configurations: 128, 1, and 32 for the L2 versus 64, 1, and 32 for the L1. Again, I'll go over what those mean later. But the long and short of it is a user-defined set of parameters for instantiating the cache that change its associativity, its size, its number of sets. And there can be different cache levels. Each of them, you can see it doesn't always have to have 2 levels. Here you have one that's just main memory and L1, right? So you get different impacts there. And the code is, so it's parameterized on what kind of caches it builds, and it models these caches. Rather, it will once you complete the project. So the only thing that's going to work right out of the box is the one that instantiates no caches at all. So we do give you code that does compile. There are a couple of warnings, but don't worry too much about those. Depending on whether or not you're running on your own machine or the ancient Red Hat machines that we have for the department, either one of those will work just fine. They'll just give you different sets of warnings. There's nothing interesting here with the C99 standard that's will have moved around on you, like with some of the people who were working with C++ on Project 1. So let's make, you can say yes, it notices that there's a stir copy somewhere here because we do get to name our caches. And there are strings that are copied, and that's not the safest thing in the world, but it's fine. We check how long the string is. And then it has some disagreements on how big a 64-bit to be printed is. Again, not a big deal. Okay. Now, if we do that and we take a look at what's now there, there's now a new binary file here, and we can make test, and it's supposed to pass the first test and fail everything else severely, right? So when we instantiate no caches, unsurprisingly, our cache code actually will work, right? So if you look at the set of files we had no output file, and now if we look, we do have an output file here. Not going to be much in it because, as I said, only the test case with a 2x2 matrix. So as a 2x2 matrix, this is the number of iterations that it runs for. This is running a 2x2 matrix multiplication once, which is not a whole lot of computation. So you can see, in fact, the total statistics for memory, main memory, were that I did 16 reads and 4 writes to multiply two 4x4 matrices by each other and then write them into a result C. So there are 3 matrices in memory, A, B, and C, and we're doing C equals A times B, right? But we'll run this some number of times to actually C plus equal. Yeah. Sorry, it's been a little while. I'll have to double check, but the particulars don't really matter because we have the reference version. So you know what the values that are actually computed are supposed to be. So if you go and look at the okay, you can see that here. Indeed, these are the final output contents of the C matrix. And indeed, these statistics here match. And they also tell you what you should expect when you run the subsequent cache versions for each of these. Now, as the matrices get larger, well, you're going to start printing more and more and more data. And so you're going to print all this cache data. The main memory is pretty straightforward, right? Although the main memory will initially be uninitialized. So anything you didn't actually compute that you're printing out of main memory is going to be whatever, it doesn't really matter. And in particular, when you look through your caches, anything where the valid bit is not set could just contain some initialized data. So that's a real thing that would actually really happen. So do ponder that, right? And yeah, so that's all in there. So all the expected outputs is there, so you'll be able to check whether or not it's in fact working. But if you're just using diff, you'll have to be a little more careful in actually combining it. Okay, so now let's take a look at what you're actually supposed to do to make it work rather than just segfault to instantiate cache. So let's take a look at what we are giving you. So if you take a look at your code here, there's not much to it. It's these, you're going to find these 5 functions. Some of these are going to be one-liners. So get index and get tag are in fact going to be one-liners. You should be able to do this in one, or if you're particularly conservative in how much you want to jam on one line, no more than 2 lines of code, right? The set sizes and offset mask fields, excuse me, is going to not require a lot of complexity, but is going to have a few more lines just because you're setting a bunch of variables. And if you're wondering, how am I supposed to know what I'm supposed to do for any of those? Well, you can go look at the header file, right? So this says that set size, offsets, and mask fields, given a pointer to a cache, the size associativity, i.e. the capacity, associativity, and block size of that cache, then you can infer the number of sets, is going to initialize, this is basically the init function, to set the following fields of the a cache struct. So it's going to set the number of ways, set the block size. Now these are, basically given, right? So you just need to pass those in. You need to compute the number of sets, right? So given the associativity, the block size, and the total capacity of the cache, you should be able to compute the number of sets. figure out the number of bits of block offset, figure out the number of bits of tag offset, right? Specifically, how much would I shift the value such that the lowest bit of the tag is at bit position 0, right? And then certainly you're gonna need an AND mask that is the size of the index field, right? So what is an AND mask? An AND mask is a collection of ones. So if my index field were 5 bits, this would be a value of 31, which is 11111, right? If my index field was 3 bits, this would be 7, right? And so forth. Similarly for the tag field. So basically, you're going to be using these for field extraction here, right? Hopefully that sort of makes sense, right? So if I set these properly, I can then, given an address, get the index field out of the address using these properties right here. Now, every set cache has its own size, its own configuration, so that's why given a cache, we're going to read its particular relevant fields and then return the right portion of the address that the cache cares about. Okay, same for get tag, just field extractions. These are 2 pair of one-liners. Write back and fill are the ones where you have to do a bit more thinking. One other piece of advice here. So you might think, oh, the number of bits of block offset is just the log of the block size, right? So I'll just call the math log function. So first no, and second no. The first no is, well, you're only modifying this .c file, and that means you're not modifying the make file, which means you're not modifying the link command, and link command does not link against math. So phooey on that. But the more important reason is that if you just try to use the default logarithm or effectively use the power function in inverse mode, either way, you're actually operating in doubles. So you're doing floating point math, and you do not want to be doing floating point math. So you probably want to write yourself a helper function to figure out how to do the log base 2 to compute block offset and tag offset. But that's, 3-4 lines of code. Okay, so where's the real interesting part going to be? It's going to be in write back and fill. How do these caches actually communicate with each other? Okay. And so let's look at what they're supposed to do, and let's look at what we've given you as a primitive that you could build the functionality onto. Okay, so write back is going to write back, right, given a particular cache, right, and the index and the way number. So basically given a particular location in that cache or something that needs to be written back, I need to write this back into the next level of memory, right? So I am giving you the cache that the line currently resides in. I need to extract all the data there and send it to the next cache. Fill is going to be reading an entire cache line from a further out in the memory hierarchy and bring it in and writing it into this location here, right? So fill, given a particular location, an index and a way number, right? We are going to place the values that it reads into this current level of the cache at this position. Okay, so everything's already been set up to figure out where in the cache you need to be doing this. You don't need to be basically implementing your own replacement functions. And let's give you an idea of what you actually have to work with. So if you take a look here at tills.c, right, this just does the printing, right? So nothing particularly interesting there, right? And a base fill for some initial matrix values. And then if you look at csim.c, right? Init cache, nothing too terribly interesting here. The ones that you're going to want to really look at is this function, perform access. Okay, so perform access does not, as caches do logically, work at block access level. This works at word granularity. Right, so this is going to do one chunk of data at a time. This is the interface that you are going to leverage to move data to or from a cache. Right, this is basically because you have a bool write right here. This is going to either read or write from a particular cache. Right, so given an access to this, right, it is going to actually go and return you that data. Now you don't need to change any of this code. It already works. It's already there, right? So there it is. That's perform access. It's already there. But do go take a look at it because this is really what you are in fact working on, and this is why you are not going to have to do anything terribly complicated in your code. Right? So again, let's go back to h. So you do not have to in fill, right? You got some cache hierarchy. Let's just say for the sake of argument, it's 20 layers deep, L1, L2, L3, L4, L5, to L19, and then the memory, right? You don't need to take care of any of that, right? All you need to do with fill is figure out how to get data from the next layer. There's always a next layer, unless you're at memory. And if you're at memory, memory will just return the data. So, that's already handled. So all you need to do is ask for, in your current level of your cache, ask the next layer to give you the data. But you're not going to have to handle the whole cache hierarchy, because if you take a look at csim.c, right, and you go look at perform access, you will find that perform access, will call the write back and fill, right, that you are going to to write. So there's going to be some mutual recursion at play here, right? So this is your interface to a cache to do a word level read or write. So you are going to need to iterate over multiple calls to perform access. Right, so you'll need a loop in each of those two that is going to, for every one of the words in a block, right? And again, the block size is variable, so that's why the interface this is sort of the fixed smallest unit of internal transfer. Then you're going to build the logical layer on top of it to transfer entire blocks at a time. Okay. Now you can also get a sort of nice sense of how the software is accessing this, right? So how does the software work? Well, you've got this load word and store word, which are just wrappers around perform access, right? So a load word is a perform access onto a cache at the address of size 8, and it is not a write. There's no value to be sent, and it's not doing block level access. It's just doing a load word. Similarly, a store word, which will initiate this whole chain, does the same, except now there's some value to be written, and it is in fact a write. So that very first one will then wander off into perform access to the cache, right? So some cache, in whatever the closest level to the processor is. Now in that very first one, you say, well, why did this whole thing work if the rest isn't implemented? Well, let's look at this line right here. If it's main memory, then you just read or write it, and you're good. Else, which is where everything else will go, well, you're supposed to be a cache, hopefully an initialized cache that actually has all of its functions defined. And so it's going to call getIndex, which you haven't written yet, and getTag, which you haven't written yet. It'll do some stuff with the replacement policy. Don't worry too much about that. You don't need to worry about how that works. That's already written for you. Okay. And yes, there are some warnings here. Do not try this at home. This is not designed to be incredibly lovely portable code. This is designed to be something to get you to understand some of the quick and dirty of be the line logic, right? Just think about how this actually works, how cache hierarchies work, remind you to get your hands dirty a bit, and then you can use this tool to explore various interactions with deeper or shallower caches. Just play around with it, right? Look at how cache simulator might work. So basically, at some point, you're going to get to the if it's a cache hit, it's going to return it because it is cache, right? Once it's properly implemented. And then the other parts are going to be the fill and the write back, right? So if there is a miss, right, then either I have some data and I need to write it back, and then fill in my my data, right? Or right, I just need to do the fill, right? So it depends on whether or not the block is dirty, right? So you're looking here, if the thing I'm trying to evict, if it's valid, then I have an eviction. I'm going to count that. If it's dirty, then I'm going to write it back to the write back, which hasn't been written yet, which we'll call perform access to talk to the next level of cache. Right. Oh, looks like there is a typo here. Fortunately, it's not actually used. So I did forget to fix that. That is an old typo. So feel free to go in and in fact, this actually compiles it. That is amusing to me. Keep forgetting to fix that. Where are you? Yeah. Okay. So there's an unused variable here. This is fine. Technically, what's actually happening here is it's assigning it to 1 in a very roundabout way because of the way the comment works. So this is perfectly legal C code, but it's clearly not doing anything useful. But as you can see, this is an unused value. So if this bothers you, feel free to delete it. Don't mind me. Anywho, I just forgotten that was had not been updated in the repo. Okay, still there in the student version. Okay, so ignoring that brief aside into my own lazy versioning. If you walk through what's going to happen here, right? So either you did the write back, or you're just doing the fill. Either way, you're going to do a fill. If you have a miss, you're going to do a fill. Always do a fill. If you have a dirty line that's being evicted, you'll be doing write back and then a fill. Logically, the write back has to happen before the fill, or at least has to have gone into the buffer right before the fill. The data has to have gone somewhere. Here, we're not modeling an explicit separate write back buffer, so it's going to literally just be simulated as happening before, but that's fine. Okay. So let's go back to what you will be doing. Right. So to walk it all through, here you're just doing some init, right? And again, you're going to want a helper function to do integer log base 2. Again, that's 4 or 5 lines. Here, you're going to, given an address and a cache, use the values that you initialized here to extract the index bits. Right? What is the value of the index? Right? So some shifting, some masking, good times. Same for tag, shifting and masking. Write back. Well, so again, this is an interface granularity question. You want to write back an entire block. You are given something that will allow you to perform accesses on a cache, i.e. to do writes into a cache. A write back is a form of write, but that are going to do that at word level. So you need to figure out how many words there are in your cache block. And then for every one of them, write the appropriate words back. Similarly for fill, there's a granularity mismatch here, right? So that's where this interface is going to fix it, right? So for every word of your block that you want to transfer, right, you are going to get it from the next level of cache. Now, again, I said that you wouldn't have to worry about whether or not there was, however many layers deep it was, because again, if you call a, excuse me, your calls into perform access will cause writebacks into the next level, which would cause a perform access into the next level, which would cause similarly a fill into the next level, into the next level, into the next level. So these things will naturally resolve. And the base case for all the recursion is right here on if a cache is main memory. So it will eventually stop because main memory is defined to always just give you the value. No virtual memory system here that you have to worry about. So it's cute, it's fun, and then once you get it working, which isn't a lot of work, then if you go look at the make file, right, then you can see a variety of different cache configurations, and you can get an interesting sense of the sorts of sensitivities to cache hierarchy that you would see for running these different computations. So if you look down there, one final word of caution: once you do get it working, this last computation here is going to run for a while. So multiplying a 256 by 256 matrix with an n-cubed algorithm is not terrifyingly fast, especially since it does it 3 times. Similarly here, multiplying 64 by 64 100 times is also not going to be incredibly fast. So you should zip on through these first few, and these last 2 will actually take a little while to compute. So I would recommend that you basically do most of your iterative debugging on these earlier ones, right? Again, obviously the very first one already works because it has no cache and works, so try not to break it. And then without a whole lot of effort, you should be able to get exactly the right values popping out for the next one. So this is actually the exact same computation you're running. So if you take a look, let me tell you how to read the output file here for purposes of debugging. Okay, so here's the first run. There's the execution line, echoed, and did it all in main memory, no cache. Great. So now here is the same computation. It's still a 2 by 2 matrix size, and it's run once. But now we have a L1, L2 in main memory. And the first thing you'll see, actually, is that the contents of main memory do not appear to be the same. That's correct. And it'll sort of be obvious why in a second. Namely, it never flushed everything all the way back out to main memory. So main memory should not have the same contents it had here, where it was doing the operations directly in main memory. The updated values are going to be living in the cache. Okay. So now you can take a look here at what actually happened. So once you have caches, the caches dump statistics, right? So here you can see we read 3 cache lines out of main memory, right? 3 cache lines is enough to read all of the matrices in question. None of the writes actually went all the way back to main memory out there. You can see that the L1 in this case doesn't have a whole lot of associativity. So there are actually some conflict misses, even though it's not really a size issue. And so you have a series of hits and misses. Some of these are cold. This doesn't classify them as whether or not they're cold or not. These writebacks do turn into accesses that are then seen at L2. So you can look at all these cache statistics. These should all be completely identical. Your cache statistics should not be changed for anything up to the size 64. When you get to size 256, because of the way this is implemented, you can actually get some variability there, depending on how the actually virtual physical mapping goes. But for up to size 64 matrices, the statistics should be identical, but the contents will be different because it actually dumps the contents of the cache. So if you're wondering, right, where are these values, right? These are the 4 output values that should have been computed. I have a 2x2 matrix, 13, 1b, 5c, and 7d are the computed values. Where are they living? And you can actually see them here. They're in this cache line right there, right? So this cache line right here, 13, 1b, 5c, 7d, that is your entire correct output matrix. It's living in your L1. That's why it hasn't been written back to memory. Now, here's the other thing to look at. Your contents of your L2, it's very small L2, right? Your L1 only had 2 cache lines. Your L2 only has 4. So, you know, that's how it goes. Note that this line here is not valid. So this means that the contents of this cache line are garbage, right? They are uninitialized garbage. And so since they are uninitialized garbage, you should ignore them, and your values may be completely different, right? So if you were trying to look at how to test this, right, you would want to ignore invalid cache lines. The valid cache lines should all have the same values. The invalid cache lines, who knows, right? So you'd have to filter that out. So it takes a little doing, but it's not too bad. So again, this gives you a complete view of all of the state of the machine, right? And then you know, main memory. Well, we're not dumping the entirety of it because that would be all of main memory. We're just dumping the contents here of the original location of the output matrix. Right, so you can say these are the places that would be written back to if we flushed everything, and they have not been because they're still living here in this cache line in L1. And so on for each of the other cases. So here you can look at the same size of matrix, and you can look at running it for a bit longer. So this is 23 multiplications. So this is just sort of amplifying the access. And you'll see here that, again, main memory just reads the one time, never has to go back out because it's a very, very tiny matrix. And here you can see that all of these are actually active when we've run through this 23 times. Again, here with here's a configuration for L2 and your L1. Okay, so it's MiniProject 2 in a nutshell. Again, once it is working, not a whole lot to do to get it working. Again, all your code just goes in here. It's none of these are more than a few lines. But to go read perform access to sort of understand how the cache is strung together, and then you'll get a sense of what you could build and do some cache simulation if you're interested in such things. Yeah, so it's a fun little exploratory tool, and nice little get your hands dirty sort of project. Okay, that's all there is to it. Especially since it's extra credit, I'm gonna stop there.